In this video, we're going to start talking about precipitation reactions. So precipitation. And precipitation reactions are going to be a type of double replacement reaction. Remember, double replacement reactions were reactions where we're swapping partners, right? I have two ionic compounds in this case, and the cation of one is going to bond to the anion of the other, and then vice versa. The thing that makes a precipitation reaction is one of our products is going to be insoluble. So we're going to have soluble reactants. So when we go through our solubility rules, we're going to find that they are going to dissociate in aqueous solution. So soluble reactants produce an insoluble product. That insoluble product, remember if it's insoluble, we put that S after it for solid, is going to precipitate out a solution. Insoluble product. So that is my precipitate. And I think the easiest way to do this is to just go through an example. So I'm going to give us a set of reactants. We're going to predict our products, and then we're also going to write ionic and netionic equations with it. We had said this was a type of double replacement reaction. So our example, we're going to write the balanced chemical equation the ionic equation and the net ionic equation. I know I haven't defined ionic equation and net ionic equation yet, but I will do that as we go through the example. When we get to that part, I'll explain what it is. So for the reaction between, and let's use lead 2 nitrate. Remember, nitrate has a -1 charge. If we have lead 2, that means lead has a +2 charge. So for my net charge on the net compound to be equal to 0, I'm going to need 2 nitrates for every 1 lead and potassium iodide. So potassium has a +1 charge, iodide has a -1 charge, so one of each when I put them together. So what I like to do to start is I'm going to separate those into ions. If we went through our solubility rules, both of those are going to be found to be aqueous. Once we start writing it out, I'll show you. But for now, what I want to do is just write them as ions. So lead 2 has a +2 charge, and then nitrate has a -1 charge. I happen to have 2 of them in this compound. I don't really care about that right now. I just want to write them as ions. Potassium has a +1 charge, and then iodide has a -1 charge. So that's kind of my work. I would just kind of have that off to the side. So my equation. I have lead 2 nitrate, and going through our solubility rules, nitrate is rule number 2. It says if it has a nitrate ion in it, it will be soluble, so it gets an AQ. We don't have any exceptions for that one. I'm actually just going to rewrite the same thing here. I just want to write it a little bit smaller because I fear I'm going to run out of room. So lead nitrate, and it's soluble, so it gets that AQ. We're reacting that with potassium iodide. Potassium, group 1A cation, no exceptions. It's also going to be soluble, so it gets an AQ. So to get my products, right, it's a double replacement reaction, so we're going to swap partners. So I'm going to go to where I wrote the ions. So the cation of the first one is going to combine with the anion of the second, right? We're going to swap partners. If lead has a +2 charge and iodide has a -1 charge, how many of each do we need when we put them together? Remembering that the number of electrons lost has to equal the number of electrons gained, right? Our net charge for ionic compounds always needs to be 0. So hopefully you guys are saying 1 lead and 2 iodide. And then I'm going to take the positive, right, the cation of my second, and the anion of my first. Remember, whenever we write our ionic compounds, we always put the cation first and the anion second. So potassium is going to be written first and nitrate second. And then since potassium has a +1 charge and nitrate has a -1 charge, we only need 1 of each to make our net charge equal to 0. Now I'm going to use my solubility rules to determine if these are soluble or insoluble. So lead iodide, rule number 3 tells me that things that have iodide in them are generally going to be soluble, but there are some exceptions, and lead 2 is one of those exceptions. So this gets an S. This is going to be my solid. This is actually the precipitate. If you were in lab and you were doing this reaction, you would take two things that just look like water, right? They'd be clear, colorless liquids, and I would combine them, and you would end up with a colorless liquid with some solid in the bottom of it. That solid that you get in the bottom is your lead iodide, lead 2 iodide. Potassium nitrate, potassium still a group 1A cation, still doesn't have any exceptions. Same with nitrate, no exceptions to its solubility, so that one's aqueous. We do need to balance this yet. Remember, all of our chemical equations always need to be balanced. I'm going to keep nitrate together when I balance it. So on my reactant side, right, I have 2 nitrates. So I need to go and put a 2 here in front of potassium nitrate. That gives me 2 nitrate ions. It also gives me 2 potassium. So I need to go back and put a 2 here in front of my potassium iodide. I'm just going to write it a little bit neater. That also gives me 2 iodide. If I go to my product side, I have 2 iodide right here. 1 lead on each side, so we're balanced. So this would be my balanced chemical equation for the reaction between lead 2 nitrate and potassium iodide. So we're going to write our ionic equation next. And what we're doing with our ionic equation is that everything that's dissociated in aqueous solution, we're going to write it that way, right? Remember, strong electrolytes don't exist as compounds. If I was to put potassium iodide in a beaker of water, I don't have potassium iodide. I have potassium ions and I have iodide ions. So for our ionic equation, all of our soluble compounds are going to be written in their dissociated ionic form. So we're going to write all soluble, right, everything that has an AQ after it, compounds as dissociated ions. I'm not going to keep Ki together. I'm actually going to write K plus and I minus. If it's insoluble, my lead 2 iodide, I'm going to keep it together. So keep insoluble compounds in their compound form. So PbI2 is still going to be written as PbI2. I know compound form, I'm kind of making up that word. But keep it together. Keep together. It's super messy. Let's actually write it in a different color anyway, because I want it to stick out. Keep together. These guys we're going to break apart. The other thing we want to keep track of is the number of moles of all of my ions. How many ions do I actually have? If you balance your original equation correctly and then you pay attention to how many of everything you have when you write your ionic equation, you will write it correctly. So when I scroll, I'm actually going to run out of room. So I'm just going to rewrite our equation down here so we can have everything in one spot. So just give me half a second. So we had lead nitrate, lead 2 nitrate, which was aqueous. We had 2 moles of potassium iodide, which was also aqueous. We formed lead 2 iodide, which was solid, plus we had 2 moles of potassium nitrate, which was aqueous. So again, this is my just regular equation. Sometimes it's called a molecular equation, which really just kind of bugs me because those are compounds, not molecules. Not that molecules are compounds, but these aren't molecules. But sometimes it is called the molecular equation. So my ionic equation, again, everything that has an AQ after it, I'm going to separate. I'm going to pay attention to how many I have. Be really careful when you're writing these also. You need to put the charge on ions. Remember, the definition of an ion is it's a charged atom. If you don't write a charge, it's not an ion, and I will mark it wrong. So if you just write Pb without the 2 plus, it's not correct. So be careful. We're going to pay attention to the charge and how many we have. So in lead nitrate, I have 1 lead. I'm going to write this pretty small here so everything fits. And it has a +2 charge. We already know the charge. If we go back up, we determined that up here, right? The first thing I did was had us write them with our charges. The charges haven't changed. I just now need to write them in that form with the right number. So back down to my problem. So lead 2 plus. This 2 here tells me I have 2 nitrates. So the 2 is going to come in front. There's no such thing as a diatomic nitrate. So I'm not going to write NO3 in parentheses with a 2. I'm going to write 2 nitrate. I have 2 potassium ions, right? There's a 2 in front of potassium iodide, plus I have 2 iodide ions. Again, all of those need to have charges. If you don't write the charges on them, they're actually incorrect. And then they all get AQs. When you're writing ionic and netionic equations for me, if you leave the aqueous off of the ions, I'm okay with that. I do want you to write the solid on the one that's solid, however. It's not a precipitation reaction if you didn't have a solid, so I do want to see that. When you're writing the regular equation, not the ionic or netionic, I do want to see the aqueous on all of them. So lead iodide, I kept it together. Lead 2 iodide, keep forgetting the 2 on you. That I kept together because it's not soluble, right? It's insoluble. And then I have a 2 in front of potassium iodide. So I have 2 potassium ions, plus I have 2 nitrate ions. And those are both aqueous. So this here would be my ionic equation, right? We took everything that was soluble and we wrote it that way. We took everything that was insoluble and we kept it together. The next thing we're going to write is our net ionic equation. And what we're doing in our net ionic equation is we're removing anything that's not undergoing a chemical reaction. Remember, a chemical change, another name for a chemical reaction, means that its chemical identity when you end is different than when you began. So if we go back up, I have 2 nitrate here, and I have 2 nitrate here. Nothing's changed. So that hasn't undergone a chemical change. It didn't react. It's just floating around, balancing out charge. So because I have 2 nitrate on both sides, we're actually going to cross them off. So in our net ionic equation, we're going to remove, and those things are called spectator ions. So we're going to remove spectator, which I spelled incorrectly, spectator ions. And spectator ions are ions that did not undergo a chemical change. Right? They are exactly the same on both the reactant and product side. So R for reactant and P for product side of our equation. If they didn't change, they're not doing anything, so we're just going to cross them right out. So if I go back up to my equation, my ionic equation, excuse me, I'm just going to look for spectator ions. So we already said that nitrate was one. So I'm going to get rid of my nitrate. And then do you see anything else that's not undergoing a chemical change? Yeah, potassium. I have 2 potassium ions and then 2 potassium ions. So what I'm going to do then is I'm just going to rewrite everything that's left. So I have lead 2 plus and 2 iodide. And that's forming lead 2 iodide, which is solid. So this here is my net ionic equation. So what we're saying is when you take lead 2 nitrate and potassium iodide and mix them together, the only thing that's happening is the lead ions are combining with the iodide ions to form lead 2 iodide. So let's go through another example. So we're going to do the same thing. I'm not going to write all the instructions again, but we're going to write the balanced chemical equation. We're going to write the ionic equation and the net ionic equation for the reaction between cadmium chloride, so CdCl2. Cadmium was one of our fixed charge metals. And let's do ammonium, one of our polyatomic ions, sulfide. So it would be really great if you guys would pause the video and work through it on your own first, and then restart it to check your work. So hopefully you guys did that and you're back to check. So cadmium chloride is reacting with ammonium sulfide. And we are going to separate those into ions. So cadmium has a +2 charge, chloride has a -1 charge. In cadmium chloride, there's 2 chloride for every 1 cadmium, but I don't really care about that right now. Ammonium NH4 with a +1 charge, and then sulfide S with a -2 charge. So when I write my products, we're going to take the positive of our first and combine it with the negative of our second, right? We're doing a double replacement, so we're swapping partners because cadmium has a +1 charge and sulfur has a cadmium has a +2 charge and sulfur has a -2 charge. I just need one of each when I put them together. And then we're going to combine ammonium with chloride. And ammonium has a +1, chloride has a -1, so again, we just need one of each. I'm going to use my solubility rules to determine if these are soluble or insoluble. If they're soluble, they get an AQ. If they're insoluble, an S. So chloride, rule 3 tells me things that have chloride in them tend to be soluble. Cadmium is not an exception, so this gets its AQ. Ammonium doesn't have any exceptions. If it has ammonium in it, it's going to be soluble. Cadmium sulfide. So sulfide is on my insoluble side of my table. It's rule number 6. It does have some exceptions, but cadmium is not one of them. So this is going to be my solid. This would be my precipitate. If we were in lab, the little solid at the bottom that we would get would be cadmium sulfide. Ammonium chloride, ammonium doesn't have any exceptions, so this is going to be aqueous. We do need to balance our equation. So on my reactant side, I have 2 chloride. I also have 2 ammonium. So if I go and put a 2 in front of ammonium chloride, that's going to balance it for us. So our ionic equation. Remember with ionic, we're going to take everything that has an AQ after it and we're going to separate it into ions. We're going to pay attention to how many we have. Anything that is insoluble that has an S after it, we're going to keep it together. So cadmium chloride is aqueous, so I'm going to separate them. I have one cadmium, which has a 2+ charge, and then 2 chloride ions. Chlorine is diatomic, chloride is not. So I'm not going to write Cl2 with a negative charge. I'm going to do 2 Cl minuses, right? I have 2 chloride ions for every 1 cadmium ion. So we're going to write it that way, 2 chloride for every 1 cadmium. In ammonium sulfide, I have 2 ammonium. So again, that 2 is going to come out in front. So 2 NH4+. And then sulfide has a -2 charge, and there's one of them in that compound. My products, cadmium sulfide is solid, so I'm going to keep it together. And then ammonium chloride, I have 2 moles of that. So 2 ammonium ions again, plus 2 chloride ions. So that is my ionic equation. My net ionic equation, I'm going to get rid of my spectator ions. Again, spectator ions are ions that are not undergoing a chemical change. They're going to be exactly the same on both the reactant and product side of my equation. So if we go up to our ionic, I have 2 chloride, and then over on the product side, I also have 2 chloride, so I'm going to cancel those out. I have 2 ammonium, and I have 2 ammonium. And then I'm just going to rewrite what's left. So I have cadmium 2+ plus sulfide, which has a -2 charge, going to cadmium sulfide solid.